So today we have two smaller topics to talk about, and this will wrap up our discussion of three-phase systems, at least from a context of sources and loads and all that kind of stuff. We're going to be dealing with transformers and then obviously three-phase transformers and stuff like that after we get out of here. But let's talk first about power factor correction. So just to remind you all, in a single phase system, we had power factor correction look something like this. So we had our single phase voltage source, VS. We might have had some sort of transmission line impedance, ZW. And then we had some load impedance over here, ZL. And if we needed to correct the power factor at which our voltage source was supplying power, which is the same thing as the power factor at which that transmission line impedance and load added together are absorbing power, we would place a capacitor C across the terminals of our voltage source, which would improve the power factor of our system. And our expression for determining C was P old multiplied by the tangent of theta old minus the tangent of theta new divided by omega multiplied by the magnitude of the voltage drop across the capacitor squared. This is what we did at the end of our discussion on single phase systems. In a three-phase system, we are going to do something very similar, except that, I hope it's fairly obvious, we are not just going to add a single capacitor into our system to correct the power factor, but instead we are going to add a capacitor bank, okay? So it will be a three-phase network of capacitors, and we'll have an option of connecting that network either in a delta configuration or a Y configuration. So let me draw what this might look like in a three-phase system. So on the left-hand side over here, I'm just going to have a generic three-phase voltage source. So this is my balanced three-phase source. Here are our transmission line terminals, lowercase a, lowercase b, and lowercase c. I'm only depicting those because we will always have access to those three terminals. We may not have access to a neutral because if it's a delta connected source, the neutral doesn't exist. And if it's a Y connected source, the neutral isn't technically necessary unless it's an unbalanced system. Similarly, over here on the right-hand side, I might have my balanced three-phase load. And then obviously connecting my source to my load will be my transmission line network. For right now, I'm going to leave it as if our transmission line network doesn't have any impedance, just to show you how the connections are going to work, but it's not going to be hard to add those things in if necessary. And so for our capacitor banks, we are going to have, like I said, two different options. So I'm going to start by drawing a Y-connected capacitor bank, okay? So I might have a node from here, jump over, and then I'm going to call this capacitance right here CY. And pretty similarly, this is going to be another CY. And then I will have a third CY right here. And I will just tie the bottom terminal of all of these capacitors together. And so this is going to be the neutral for my capacitor bank. Okay? So the neutral for this capacitor bank does not have to be connected into another neutral into our system, literally at all. So even if both our source and our load were connected in delta, we could still connect our capacitor bank in Y, because there's just going to be a local neutral there that's serving as the connection point for that terminal of all three of those capacitors, right? So that's how our Y connected bank might be configured. And for what it's worth, in this particular case, right? So the voltage drop across our capacitors would be let's say the magnitude of the voltage drop across our capacitors would just be VAN or VBN or VCN, because those are all going to have the exact same magnitude, right? So we would just use that line to neutral voltage in order to calculate the value of the capacitor that is necessary. The alternative is a delta connected capacitor bank. And in a delta connected capacitor bank, we're going to have something like this. So we would have some capacitance C delta seen between the A and B phases of our transmission line, a second capacitance C delta seen between the B and C phases, and lastly, a third delta connected capacitor, this is C delta, between the A and C phases. And the voltage drop across these capacitors would just be the magnitude of VAB, our line-to-line voltage, because each of the capacitors is connected between the transmission lines. So these are our two options. We'll explore some examples and all of that kind of stuff to see how this will work here in just a moment. Okay. So you might be asking yourself, and we'll see how this plays out with the math in a moment, why we might ever choose a delta connected bank versus a Y connected bank or something like that. So each of these capacitors, we're going to see that one of the capacitors is always going to be larger than the other. I don't exactly remember if it's the Y connected capacitor is, I think it's always 3 times smaller than the delta connected capacitor, but we'll sort that out in a minute. But these capacitors are going to see different voltages, right? Because the line to neutral voltage is a square root of 3 times smaller than the line to line voltage in this system, 100% of the time, right? So I don't know how many of you guys have ever had to go out and buy a capacitor for anything at this point in your careers. Might not be many of you, but capacitors are rated based on the amount of voltage drop that they can see, right? So essentially, because the delta connected capacitors have to see a higher voltage, they might be slightly more expensive. So it's really just going to be a cost analysis that tells you which particular type of capacitor bank that you should connect. Can you get larger, cheaper capacitors that see a smaller voltage, or can you get less expensive, smaller capacitors that see a larger voltage? And whichever one comes out to be the most cost savings is the one that you will go with, kind of thing. Okay. All right, so before we get into working any example problems on this, because we've already done the overwhelming majority of the legwork in a single phase system, the one thing that I want to make abundantly clear is that in order for us to apply this equation for C from our single phase relationships, the only thing that we need to change is to make sure that we're looking at P old on a single phase basis, because we are choosing a capacitor that will correct a single phase of the system and then just adding the two other identical capacitors to correct the rest of the system, right? So we are actually going to largely approach this on a single phase basis. So to see what I mean by that, let's look at your in-class assignment problem number 1. Okay. So in this first problem, we are told that we have a balanced three-phase source, and it's supplying a balanced three-phase load, which is drawing a total of 20 megavolt amperes at a power factor of 0.8 lagging. Okay. We are told that the line voltages at our loads is 4.6 kilovolts RMS, and our excitation frequency for our system is 60 hertz. And we are asked then to determine the size of the capacitors needed to correct the power factor to 0.95 lagging if the capacitor bank is connected in Y, and then also if the capacitor bank is connected in delta. So I'm going to just draw a little picture of what's going on here. So over on the left-hand side, we've got our balanced three-phase source. And we don't really know much information about it at all. Over here on the right-hand side, we've got our balanced load. And we are told that our load draws 20 MVA at a power factor of 0.8 lagging. And we are told that the line voltages at our loads, so that would be this voltage here, has a magnitude of 4.6 kilovolts RMS. We're also, so let me just write some things down here. So VLL, the line voltage at our loads, is 4.6 kilovolts RMS. Our frequency is 60 hertz. The magnitude of the complex power absorbed by our loads is 20 megavolt amperes, and PF new, what we're aiming for, is 0.95 lagging. Okay. And ultimately, we are going to use the following equation. C is equal to P old times the tangent of, theta old minus the tangent of theta new divided by omega times the magnitude of the voltage drop across the capacitor squared. So using the information that we were provided, how are we going to find P old and theta old? So theta old is just inverse cosine of the power factor? Sure, absolutely right. Okay. I'm going to call that PFL. So that would be inverse cosine of 0.8, which should be 36.87 degrees and some change. I'm going to wind up storing that in my calculator as X here in a moment. Okay. How am I going to find P old?
Um, never mind, I forgot.
So let me ask you guys what I hope is a simple question. Do we have enough information to calculate the total complex power absorbed by our load? We have the apparent power and we have the power factor, so I think we do, right? So we could say that the total complex power absorbed by our load, I'm just going to call this SL, is just going to be 20 MVA with an angle of the inverse cosine of 0.8. That's our power factor. And so that's going to come out to be 20 angle 36.87 degrees megavolt amperes. Let me throw that into my calculator real quick, just so I can do the conversion. And in rectangular form, that comes out to be 16 plus J12 megavolt amperes. So which one of those numbers is the total average power? The 16, right? So essentially, this guy right here is P three-phase. Well, P old, just to make this abundantly clear, is the power absorbed by a single phase, because we're finding the value of a capacitor for each phase. So I hope to God this isn't a hard question, but how am I going to take that 16 volts for all three phases and figure out how much is absorbed by each phase? Divide it by 3, because it's a balanced load, so they're all going to absorb the exact same thing. So from this, we could say that P old is just 16 thirds of a megawatt. And that is literally just taking the three-phase power, average power, and dividing it by a factor of 3, so that we have the power absorbed by each phase. Okay. Okay. So how are we going to find theta nu? Sure. So theta nu is just going to be the inverse cosine of 0.95, our new power factor, right? Which I get to be 18.195 degrees, and I'm storing this in my calculator as Y. And I did wind up storing that as X. Cool. What's omega going to be? Exactly right. So omega is equal to 2 pi f, and since f was 60 hertz, this is going to look like 120 pi radians per second. So this is where things start to get a little difficult, because the voltage drop across our capacitor, which is the only thing that we have left to figure out to calculate C, is actually going to be different depending on if we have a Y connected load or a delta connected load, right? So let's figure that out over here, okay? So the magnitude of our voltage for VC for a Y connected load. So what voltage information do we have? The line voltage of 4.6 kilovolts RMS. So would that be the voltage for the Y connected load or the delta connected? Delta, okay. So how are we going to convert that voltage to be appropriate for a Y connection?
Divide by √3.
Divide by √3. And since we're only worried about the magnitude, we can just divide by √3 and not worry about the angle, right? So this is going to be just 4.6 kilovolts RMS over the square root of 3. Which I get to be 2.65, let's see, 2.656 kilovolts RMS. I'm going to store that as Z just to make my life slightly better. And the magnitude of VC for delta is just going to be the 4.6 kilovolts RMS because we already have a line-to-line voltage given to us. So I don't need to do any work for that. Okay. So putting these pieces of information together, CY is going to be 16/3, and I'm just going to do times 10 to the 6th watts here, multiplied by the tangent of theta old, which was 36.87 degrees, minus the tangent of theta new, which was 18.195 degrees, all divided by 120 pi times 2.656 volts RMS squared. So if I throw this into my calculator, 16/3 times 10 to the 6th, multiplied by the tangent of what I have stored in my calculator as X, minus the tangent of what I have stored in my calculator as Y, divided by 120 pi times what I have stored in my calculator as Z squared, I wound up getting 0.000845,047 farads, or 845.047 microfarads.
The 6, is that because
We're in mega, yeah. And, oh, sorry. That technically should be kilovolts RMS right there, but I had it in my calculator as 2,656 and change volts RMS so that I knew the units would work out the way that I wanted. So I put it in base units to make sure and then converted at the end. Okay. So for C delta, it's going to be effectively the exact same thing. 16 thirds times 10 to the 6th watts. Tangent 36.87 degrees minus the tangent of 18.195 degrees. All divided by, 120 pi times 4.6 kilovolts RMS. So let me just go back up to here. And where I had Z, I'm just going to type in 4600. And I wind up getting 0.000281682 farads, or 281.682 microfarads. Ricky.
So is A and B like them hooked up at the same time, or is it just like one or the other?
It's one or the other. So you either have a Y-connected capacitor bank to hit a target power factor of 0.95, or you have a delta. You wouldn't probably do both. So any other questions about these calculations? Okay, so I want you guys to do me a favor real quick. What's the relationship between CY and C delta? Like, what's the ratio of those two things? Throw it in your calculator. It's not root 3. Three. Okay. Anybody care to venture a guess as to why it's 3? You look very excited with yourself. You guessed. Okay. So you guys remember the delta Y transformation for loads, right? Or impedances. Okay. So go from a delta connection, a delta connected load, to a Y connected load. We divided our impedance by a factor of 3. Well, what we just found is that C delta is actually CY divided by 3. So that factor of 3 is there, but it seems like it's backwards, because usually for us to go from Y to delta, we would multiply by a factor of 3. Okay. The reason why it's backwards for capacitors is because the impedance of a capacitor is 1 over omega C. So we're going to have an inversely proportional relationship. So to go from CY to C delta, we're going to divide by 3, but to go from ZY to Z delta, we would multiply by 3, because once again, a capacitance's impedance is 1 over J omega C. Okay. So it's still the factor of 3 that we would get doing a load transformation. We just have to do it opposite the way we're thinking of, because the impedance of a capacitor is inversely proportional to the capacitance value. Okay. Or you can just change the voltages and do it that way. But I'd like to at least make you aware of this, so that technically speaking, if you know one of the capacitor values, so if you know CY or C delta, you can easily get the other one just by transforming it without having to do any extra work. All right, so any questions about this problem? So let's look at problem 2. Similar thing, but a little bit more difficult, okay? So in this guy, we're told explicitly that we have a 3-phase source that is Y connected, and our phase voltage on the A phase is 220 angle 0 degrees volts RMS, and we are supplying a Y connected load that is absorbing 50 kilowatts in each phase at a power factor of 0.8 lagging. There are 3 capacitors that were found, and each of those capacitors has an impedance of negative J2 ohms at whatever the system's operating frequency is. We are asked to determine the power factor of the combined load. So that is meaning the capacitor bank and the balance load if the capacitors are connected in a Y configuration or a delta configuration. Okay. So I'll draw a picture of this system like we've done it before. Okay. So I was actually told what type of voltage source I had, so I guess I'll draw that out. There's no mention of any specific transmission line impedances, so I will, goodness gracious, choose to just connect these guys with a wire. I've got my load over here. I'm going to call this ZY, which, to be clear, we are not given. And then in part A, we are told that we have a Y connected capacitor bank. So essentially that means that in parallel with each of those ZYs, we would have a minus J2 ohm capacitance. Like so. Okay. And our goal here is to figure out in part A at what power factor our system is operating. Okay. So let me just write down our given information here. So VAN is 220 angle 0 degrees volts RMS. Excuse me, P three phase is equal to 50 kilowatts. PF is equal to 0.8. ZC is minus J2 ohms, and I think that is pretty much it. Three phase. So that 50 kilowatts is the total amount. Hold on, actually, that's not true. Supplies 50 kilowatts of power in each phase. So this is the power for a single phase of our load. So I am of the opinion that it would be pretty darn handy if we were able to figure out what that impedance ZY is, because that would make this a fairly simple and straightforward thing, right? Then we could just lump those impedances together, find the equivalent impedance, and then if we know the equivalent impedance, the angle of the equivalent impedance is going to give us our power factor that we're interested in, right? Because the angle of the impedance is the same thing as the power factor angle. We talked about that when we're looking at single phase systems. So does anybody have any thoughts on how we might figure out what that impedance ZY is? So ZC less so, but VAN absolutely. Okay. So it's going to be hard for me to draw it on here, so I'll do it on the C phase because there's more room. But what do you think this voltage VCN is going to be? So it'll be, what I'm trying to get at here is because we don't have any transmission line impedance, so there's no ZW. ZY is going to see the same thing as our phase voltages of our source. So we know the voltage drop across that impedance ZY, right? So we know it for the A phase, the B phase, and the C phase. So the only other thing we would need to know to calculate that impedance would be the current flowing through each of those phases. So any thoughts on what we could do in order to find our current? So the power absorbed by the load is going to be related to both the voltage drop across the load and the current flowing through the load. So we could say that, let's say, the complex power absorbed in the A phase is nothing more than the voltage VAN multiplied by the complex conjugate of the current IAN, right? So we're just going back to that single phase complex power fundamental relationship because we have enough information for most of that. So VAN was given to us. We're essentially trying to find IAN, but to do that, we need to know what SA, the complex power absorbed by the A phase, is. How might we figure that out? Okay, so SA, so we have the power factor. What else do we have? The average power per phase, right? So recall that that's going to be our single phase average power divided by our power factor with an angle of the inverse cosine of our power factor. This is literally what we did back when we had single phase circuits, right? So that's going to look like 50 kilowatts divided by 0.8 with an angle of, excuse me, the inverse cosine of 0.8. So 50 over 0.8 angle inverse cosine of 0.8 gives me 62.5 with an angle of 36.87 degrees kilovolt amperes. And now I can rearrange this expression over here to find that IAN is going to be just SA conjugate over VAN conjugate, right? Where all I did was divide both sides by VAN and then take the complex conjugate of both sides, because as we learned when we were talking about our single phase system, the conjugate of the conjugate is just the original thing itself, because we're just switching the sign on the angle and then switching it right back. So that's going to look like 62.5 with an angle of 36.87 degrees kilovolt amperes. Sorry, and that angle should be negative because I needed to do the conjugate, divided by 220 angle negative 0 degrees volts RMS. So the conjugate of my answer, and I'm going to multiply that by a factor of 1,000 to get rid of getting an answer in kiloamps, divided by 220 gives me a current of 284.091 with an angle of negative 36.87 degrees amps RMS. So did anybody else get a similar result? Let's start there. Wyvern's giving me a thumbs up. So from here, I think we could safely say that ZY is just going to be the voltage VAN divided by the current IAN. So that's 220 angle 0 degrees volts RMS divided by 284.091 angle negative 36.87 degrees amps RMS, which I get to be 0.774 with an angle of 36.87 degrees ohms. Or if we wanted it in rectangular form, which I don't think we actually matters, but I've already started doing it. This would look like 0.619 plus J 0.464 ohms. So in part A, now that we have ZY, and we know that our capacitors are just connected directly in parallel, right? Because it's a Y-connected capacitor bank for part A. We could find that equivalent impedance. So that's just going to be ZY in parallel with minus J2 ohms. So I'm just going to take that answer and say that answer times minus 2I over that answer plus minus 2I. And I get 0.935 and some change with an angle of 14.896 degrees ohms. And from this, the power factor with the capacitor connected, capacitor bank connected in Y is just going to be the cosine of this 14.896 degrees. Because once again, the angle of the impedance is the same thing as the power factor angle. So because I know what the my impedance is in polar form, I can just calculate my power factor directly. So cosine of that angle gives me 0.966. Is this a leading power factor or a lagging power factor? Lagging because the angle is positive. Okay. For part B, now I need to figure out what's going on. By the way, we got it right. Now I need to figure out what's going on if my capacitor was connected in delta. So we have two ways that we can approach this. We could either transform that delta connected capacitance into a Y connected capacitance. Since we know what the impedance is, that would just be dividing minus J2 ohms by a factor of 3, and then finding out what those two guys look like in parallel. Or alternatively, we could convert our ZY into a delta connected impedance, which would just be multiplying ZY by a factor of 3, and then putting that in parallel with the minus J2 ohms, and then using that impedance. Either way is going to give us the exact same result. I'm going to choose to just convert ZY into a delta connected impedance here. So I can leave that J2 alone. Okay. So ZEQ is just going to be Z delta in parallel with minus J2 ohms, which is the same thing as 3 ZY in parallel with minus J2 ohms. And because I already have most of that in my calculator, that's going to make this really easy. I just need to put a 3 in front of what I have for ZY. I wound up getting an equivalent impedance of, there we go. Sorry, my stylus didn't want to write for a moment. 2.377 with an angle of negative 35.069 degrees ohms. And so the power factor for our delta connected capacitor bank, or the power factor of our system with the delta connected capacitor bank, is then the cosine of that negative 35.069 degrees. Which I get to be 0.81846 and some change. Is this a leading or lagging power factor? Leading because it's negative. And that is indeed the correct answer. For what it's worth, that is one of multiple different ways that we could approach this problem, but that's probably the most straightforward path. So that's why I chose to do it this way for you guys. All right, so before we move on from this, does anybody have any questions about this? All right, so then the last thing that I want to talk about for today, and there is a problem associated with it, but I need to introduce the topic itself, is how power is actually measured in three-phase systems. And for what it's worth, when you guys take the 361 lab next spring, you will literally be doing exactly what we're talking about today on physical systems. Okay. So in order for us to understand how power is calculated in a three-phase system, it might be useful for us to understand how power is calculated in a single-phase system, and then we can adapt from there, essentially, okay? So in a single-phase system, we use what is called a watt meter, okay? A watt meter is just a device that measures the average power absorbed by a load, okay? The watt meter contains two coils. One is the current coil and the other is the voltage coil. And essentially, depending on how much energy is stored in those coils, it causes a needle to deflect, and that needle tells us what the actual average power absorbed by that system is. Okay? So if I had a basic single phase load, right? So let's say that I have a system like this, okay? So this is part of some larger overall circuit. Here's terminal A for my load. Here's terminal N for my load, because in a single phase system, we're going to be between a hot wire and a neutral, okay? This is going to be my current coil, so that's why it's designated CC. This is going to be my voltage coil. That's why it's designated VC. And I'm going to put an indication here. So we have a choice as to whether we want to connect the positive polarity terminal of the current coil or the negative polarity. And we also have a choice as to whether we're going to connect the positive polarity or negative polarity terminal of the voltage coil. And these two coils added together is actually our watt meter, which I'm just going to call here WM, standing for watt meter. Okay. And this watt meter returns the power absorbed by whatever load is connected. So I'm going to continue on and draw some things here. Over here on the right, I will have whatever my load is. And so I'm just going to designate this as my load, which has some impedance of ZL that we may or may not know. And for what it's worth, if we were so inclined, we could measure the magnitude of the voltage drop across this load using literally just a multimeter and the current flowing into this load, or at least its magnitude, also just using the multimeter, right? So the volt RMS setting and the amp RMS settings on our multimeter are literally giving us, or could literally give us the magnitude of both that voltage and current if we were so inclined. But the watt meter is the thing that's going to tell us the average power that's absorbed, which is usually what we're interested in because that's what we're paying for. Okay. So this is our setup for a single phase system. We could pretty easily adapt this to a three-phase system, and it might look something like this. And I'm going to put this as three-phase system number one, because we're going to explore a few different connections that we can use. So this three-phase system number one is literally just exact same thing we've done up here, except applying it, to all three phases. So we might have something like this. So here's our current coil on the A phase. And then our voltage coil on the A phase. Down here is going to be my B terminal line. So here's my current coil on my B phase. And my voltage coil on my B phase. Down here is my C phase terminal line. Once again, current coil and voltage coil. And then down here is my neutral. And so let me jump this guy over. So essentially, I'm going to have to tie the negative polarity terminal or the bottom terminal of the voltage coil down to this neutral connection on each phase. And then I'm just going to extend these wires way over here to connect my actual load. ZYA, just in case we don't have a balance system. ZYB, ZYC. Neutral like so. And just putting boxes around our watt meters. This is watt meter number 1. And it's giving us the average power absorbed by the A phase. This is watt meter number 2, giving us the average power absorbed by the B phase. And watt meter number 3, giving us the average power absorbed by the C phase. So in this system, the total 3-phase power absorbed by our load is just going to be the readings of watt meter A, B, and C, where these 3 watt meter readings are essentially the phase voltage for A multiplied by the phase current for A times the cosine of the angle of ZYA plus the phase voltage for B times the phase current for B. Sorry, that should be a lowercase. No, that should be uppercases. Sorry, that's on me. Cosine theta ZYB plus VPC IPC cosine theta ZYC. So to briefly recap what we did here, we literally just took our single phase watt meter and replicated that 3 times, one on each phase. Does anybody see a problem with this? Or problem might be too strong of a word. Potentially a drawback to this, or maybe something that is of concern.
Need to know a lot of different variables.
So we don't necessarily need to know a lot of different variables because that piece of equipment is going to tell us those powers, and I'm just giving you an idea of what math it's essentially doing. The problem is that we have to have access to the neutral on our load, which means this method will only work for Y-connected systems where we have access to a neutral. So if we have a Y-connected system like synchronous machine, where we don't have access to its neutral terminals, we only have access to the phase terminals, we couldn't use a 3-watt meter method. If we have a delta connected literally anything, we also can't use 3-watt meters like this because they require us to have access to a neutral that literally does not exist. So in order to avoid this, there is a way that we can connect our watt meters just having access to our transmission line terminals, which we will always have access to on any 3-phase system because that's how we connect it to our 3-phase source, right? So that method is what's known as the 2-watt meter method, and it's the one that's actually used in industry fairly regularly. So here's 3-phase system number 2, aka the 2-watt meter method. And so I've got my A terminal here, my B terminal here, my C terminal here, and I'm going to intentionally not use the neutral terminal even if it happens to exist. And so what I'm going to do is something like this. So I'm going to put my current coil on the A phase line for wattmeter 1. And I'm going to put my voltage coil between the A phase line and the B phase line, right? So the only thing I have to have access to connect this wattmeter is the A phase terminal and the B phase terminal, right? So here is wattmeter number 1. And this is going to give me access to a power I'm going to call P1. And I'll need to explain what P1 is here in just a moment. And on the C phase line, I'm going to connect my current coil. And then between the C and B phases, I'm going to connect my voltage coil, like so. So down here, I have wattmeter number 2. And this is telling me some average power P2. And then over here to the right is my load. And so this is my, actually, I'm just going to write it as 3-phase load. I'm going to put in notes here, Y or delta, because it doesn't matter. As long as I have access to those 3 transmission line terminals, it's going to work. And I'm also going to make a note, it doesn't matter if this is balanced or unbalanced. The 2 wattmeter method will still work. So it is a very, very powerful technique. Okay. I'm going to take note of a couple of things. So the first of which should be, I think, fairly obvious, that volt coil is essentially reading the magnitude of VAB. This guy is essentially reading the magnitude of VBC. The current coil for wattmeter 1 is essentially reading the magnitude of IAA, and the current coil of wattmeter 2 is essentially reading the magnitude of line current ICC. So if we assume a balanced load, our power P1 is just going to be the magnitude of VAB, which is our essentially a line voltage, times the magnitude of IAA, which is a line current. And then we're going to have cosine of theta z plus 30 degrees. So I'd like to talk where this plus 30 degrees bit comes from, okay? So essentially this plus 30 degree bit comes from the fact that if my load is connected in, actually connected in Y, then the voltage VAB there is 30 degrees out of phase with the actual voltage drop across that phase of my load, right? Because we know that to go from that phase voltage V capital A capital N to line voltage V capital A capital B is multiplying by √3 angle 30. So that's one possible way that 30 degrees right there can manifest. The other way is if I have a delta connected load, then that VAB up there represents my phase voltage, but IAA is not my phase current. We know that that IAA is going to split into IAB and IAC, and that also has a phase difference of 30 degrees that we've explored previously in this class. So regardless of how my load is connected, I'm actually going to see cosine of whatever the impedance of my load is plus 30 degrees because I've got a mixture of line quantities and phase quantities depending on what type of load I'm looking at, okay? Pretty similarly, we could say that P2 is going to be VBC ICC cosine theta Z minus 30 degrees. And this minus 30 degrees is coming from the fact that we're looking at essentially the phase voltage on the second phase, but the line current on the third phase. And so that's going to shift that guy around, okay? Same basic reasoning, but the negative sign is because we're looking at them across different phases, okay? So if we were to add these results together, what we would get is a total power, which I'm going to call it P sub T. That is the magnitude of VAB times the magnitude of IAA cosine theta Z plus 30 degrees plus the magnitude of VBC times the magnitude of ICC cosine theta Z minus 30 degrees. And if this is a balanced system, the magnitude of VAB and the magnitude of VBC are the same thing. The magnitude of IAA and the magnitude of ICC are the same thing. So really, we've got just a trig identity essentially to deal with. I'm not going to bore you guys with that, but what it comes out to be is twice the magnitude of VAB times the magnitude of IAA times the cosine of theta Z, our actual impedance of our load, times the cosine of 30 degrees. So, before I ask you guys to do it, yep. What is twice the cosine of 30 degrees? Square root of 3. So this comes out to be, so 2 times the cosine of 30 degrees is root 3. VAB is a line voltage because it's measured from line to line, regardless of whether we have a Y-connected system or a delta-connected system. IAA is a line current. So what's this? Or actually, I guess I should say, does that look familiar? Because it's literally the equation that we derived in our last class meeting for the average power in a three-phase system. So essentially, even though I'm only using 2 watt meters and I have them connected in this weird configuration where I'm not measuring the power per phase, I'm just adding these 2 powers together, it actually comes out to be the total 3-phase power if I set my watt meters up in this kind of awkward looking configuration, okay? For what it's worth, we derived it here for a balanced load. but it 100% works in an unbalanced load as well. But let's take this a little bit further, okay? So if we continue on with our assumption of a balanced load, we can also figure out what our power factor is going to be, okay? So we know that adding the results of our 2 watt meters together, adding the output of our 2 watt meters together, looks like, I'm going to do it like this, VL times IL times cosine of theta z multiplied by a factor of twice cosine 30 degrees. If I take the difference of the reading of my 2 watt meters, and again, I'm not going to bore you with the trig identities, this actually comes out to be VL IL sine theta z times a factor of -2 sine 30 degrees. And so what I could do is I could take the ratio of these two mathematical operations, right? So P1 plus P2 over P1 minus P2 is going to look like VL cosine theta z times twice cosine 30 degrees over VL sine theta z times -2 sine 30 degrees. And let's play around with this just really quickly here. So I've got a VL times IL in my numerator and a VL times IL in my denominator. So those guys cancel each other out. I've got a 2 up here and a 2 down here. So those guys cancel each other out. And so what I wind up getting here, I don't know how strong you guys' trig background is, but do you guys remember that sine over cosine is tangent? Okay. So I've got cosine over sine, so that's 1 over tangent of theta z. And I want you guys to put cosine of 30 divided by negative sine of 30 in your calculator and tell me what you get. -√3. So this whole big gross thing comes out to be -√3 over the tangent of theta z. And so if I know those two readings are related to the tangent of theta z, then I could find from this that theta z is just going to be the inverse tangent of √3 times P2 minus P1 over P2 plus P1, okay? So for what it's worth, I'm getting rid of that negative sign by switching the order of my subtraction, right? So if P1 minus P2 comes out to be -2 sine 30 degrees, then P2 minus P1 would be +2 sine 30 degrees, which I guess I should have written down that in my notes and it made it less confusing from the jump, but anyway. And then from here, our power factor is simply the cosine of theta z. Now, one pretty awesome, in my opinion, result of this relationship is A, we just have two measurement devices. They're giving us powers. And we can use those powers that they output to calculate not only our total average power, we can also use it to calculate theta z. For what it's worth, the inverse tangent operation on your calculator can actually return negative numbers. So we will have a real depiction of whether our power factor from calculating this is going to be leading or lagging, because the angle we're going to get will actually indicate whether we have a leading or lagging situation. Another interesting thing about this is we can use those 2 watt meters to calculate power, and we can use those 2 watt meters to calculate power factor. We can use those two things to calculate our complex power for our system as well. So realistically, just having these 2 watt meters connected this way tells us every possible thing we could need to know about the power or complex power being absorbed by our system, because it gives us average power and power factor, and we can use that to construct the complex power, which then gives us our apparent power and our reactive power, the only two missing quantities. So this is a very, very powerful method for knowing literally everything that's going on in a 3-phase load, particularly a balanced 3-phase load. We can only figure out total average power in an unbalanced load, but that's still rather useful. All right, so to wrap things up here, let's look at ICA problem number 3. Okay. So we're told specifically that we have a balanced 3-phase load and 2 watt meters. The first is reading 60 kilowatts and the second is reading 180 kilowatts. From these pieces of information, we are asked to determine the average power absorbed by the load P3 phase. So our total average power is just going to be P1 plus P2 is equal to 240 kilowatts. Nothing remotely difficult about that guy, right? For part B, we're asked to find our power factor. Well, we know that our power factor is just equal to the cosine of theta z, and we learned that theta z can be determined by doing the arctangent of root 3 times P2 minus P1 over P2 plus P1. So that is going to be the arctangent of the square root of 3 multiplied by, so let's see, P2 minus P1. So 180 minus 60 is 120. And 180 plus 60 is 240. So that's literally just root 3 times a half. So inverse tangent of root 3 times 1 over 2, I got to be 40.893 degrees. And then if I do the cosine of that answer, I get a power factor of 0.756. And it'll be lagging because theta z was positive. And then finally, I can calculate my complex power the exact same way we've done it 30 times at this point in this class. S3 phase is just going to be P3 phase over our power factor with an angle of the inverse cosine of our power factor, which by the way is just theta z, right? So that's going to look like 240 kilowatts divided by 0.756. That looks too much like a 2 for me, with an angle of 40.893 degrees, or 317.490 angle 40.893 degrees kilovolt amperes.